Okay, so we should be alive, not only alive, but also live. So welcome to the first lecture in software testing. And this is in two parts. So the first part is the course introduction for the course. And then we're going to have the first lecture, which is called the Basics of Testing. My name is Daniel Toll, and this is the things that we're going to progress through. And yeah, so I'm a programmer. I've been programming since I was 12. I am 45 today. During programming, I mean, you always sit on at least 2 chairs when you're programming. So as a programmer, I'm also a tester. I was programming computer games for a number of years. That was my main goal when I wanted to become a programmer. I wanted to become a game developer. So I have produced a couple of games and also taken the lead development or programming for a couple of games. I am also a computer science researcher, so I've published a couple of papers on different topics, including computer science education and also code quality. In my spare time, I take care of my family. I like to do CrossFit, and I'm also a painter, so you can see one of my paintings here. This lecture is gonna be with 95 students and then me. So in order to be able to manage that communication load, we need to have a communication strategy, and everyone needs to accept and follow that strategy. So let's first see if I am broadcasting sound online, because that would be awesome. If you can hear me on YouTube, you can answer either through the YouTube comments or in Slack in the thread of the announcement, the lecture announcement. Let's see if someone answers. Oh, awesome. So we have a number of different things in our communication strategy. The first one is the course homepage. So there is a link to the course homepage on top of the Slack channel. And the course homepage are for static things. So things that do not change over the course or between courses. It includes recorded lectures from previous years. So if you need, if you miss a lecture and you want to listen to it before it's given, then you can listen to previous year's lectures. There might be minor changes, but I do not foresee any large changes. It also includes links and lectures that is only going to be provided pre-recorded. So there are some guest lectures and stuff like that. It also contains assignment descriptions. And yeah, so I try to put everything that does not change there. Then in the schedule, you have the lectures and the tutoring sessions, and also deadlines and exams. So I've given on Friday, I gave the list of exams and deadlines to the administrator to put in the schedule. So I hope that will be done soon, so that you can also put it in your schedule. When it's done, I'm gonna write in Slack. So Slack, since we are students here in Kalmar, in Växjö, and also online, then we need one place of communication. So Slack is going to be that. And yeah, think Slack. If you're going to contact me, then it's Slack. If you're going to ask a question about an assignment, then it's Slack. Yeah, use Slack for everything. I would say every communication. I'm not sure. There might be a My Moodle forum. We're not going to use it. I'm not going to check it. I'm not going to answer it. So Slack it is. Email. Yeah, you can use email for official things, but always ping me in Slack if you've emailed me. So generally, it takes a couple of more days for me to answer an email, and I often forget to check them because I want every communication for Slack. But there might be things that, unregistering or sick leaves or things that are more, let's call it legal things. where you really want it to be saved forever, because everything you email is saved forever, right? Because then you're emailing a government institution, and then everything is archived and things like that. So if you're doing something that is, potentially important for you, like unregistering or something like that, or then that's going to be for email. But always also communicate to me through Slack. Okay. The course homepage contains a lot of different things. So up in the right-hand corner, there is the study guide, so you can read the communications strategy. Some information about the assignments and how they are graded, what we expect from you, and then we have weekly study guides. So these are based on the last year's, and if you scroll down, you can see that the recording here is from, so this is the recording from last year, and then also some older recordings that I'm not going to reproduce this year, so you can still listen to them. There are also some external resources that I think that you should go through, and a guest lecture by Max Beppe. He's freelance developer. He studied at Linnaeus University 2015 to 2018 or something like that. And you can see every week has all of these things. So if you want to know what am I going to do this week, then check it here. It also contains reading instructions. So first week, 3 chapters of the book. Course content. So previous year's lectures. I'm going to put this lecture and other lectures here when it's done. But you can get access to it directly through YouTube on the same link that was given for this live event. So the course literature, the developer testing. I've heard that it's hard to get, but at least I've seen that there is an ebook that you can buy, worst case. Usually students find resources anyway, but there is also an optional book, and this, if you're taking this course for a higher grade, I would recommend buying this book also. This is primarily important in the beginning of the course, and it's a good book, so it's also easy to read. So get both if you're going for higher grade. Get this one if you're only going for passing grade. Okay, there are some external resources. So I am not an expert in every part of testing. So I have collected a couple of links for different external resources, like James Bach on exploratory testing. He's quite fun. So that is why I also. And then some Google Tech Talks about agile testing. I think that is pretty old recording, but it's still a good recording, and that is why I keep it. So there are a number of these external resources. And then we also have a couple of guest lectures from 2020. During COVID, I was, working from home and feeling very alone. So I contacted a number of people to ask them to give guest lectures. So do listen to all of these in time. And then we have also a test-driven development guide, and And finally, assignments and examinations. This is the overview of the examinations. What happens if you miss a deadline? If you fail an assignment, this will happen. If you plagiarize, this will happen. And then the descriptions of the different assignments. So the first assignment is going to be handed over to you this week, and probably on Wednesday. So you're going to get a link to the first assignment for your email on Wednesday. I'm going to announce it on Slack. If I can do it earlier, I will try to do it earlier. But today is lecture day, and tomorrow I'm going to Växjö to give the same lecture, the same course introduction and the basics of testing tomorrow. So just in order to reduce my stress a little bit. So the first assignment, and then the second assignment, or it's not a second assignment, it's actually the first assignment, but part 2. And this is for higher grade. So if you're only going for passing grade, you can do the first one, But if you also want to go for high grade and also learn a lot more about unit testing, then this is the one that you're going to do also. So you need to do both. Then we have, and the second assignment can be done either alone or in pairs. Yeah. So, and then we have the assignment 2, and that is a huge assignment. So it's a big one. So you need to start early. So if you're going to need to start before Christmas, and then it's going to be presented after New Year's. And we also have a third assignment, and then we have a final exam. Yeah, so all of that static information on the course homepage. It might be that things are, even if I think that that should be static, there might be dates there from last year. So just ping me on Slack and tell me that this needs to be updated. We've had some trouble, and that was during last week, or I had some trouble updating the course homepage during last week because things rot when you're not updating them. But I think I should be able to update it now. So just tell me if something does not look correct. Okay, in the schedule, note that there are different course modes. So this is given in Kalmar and online, and almost everything in Kalmar is also online at the same time. And then we have Växjö. And I'm going to give this lecture in Växjö also, because I want to meet the students in Växjö. And then I'm going to have tutoring sessions in Växjö. But this is the only lecture that I'm giving in lecture. So the Växjö students is going to listen to these recordings also, or live events. Just before the lectures, like I did today, I'm going to put a link on Slack. And most lectures, or every lecture except the one tomorrow, is given in Kalmar. Asynchronous tutoring, when you ask questions when we don't have a session, you ask it through Slack. And that should happen in the course channel in Slack. Yeah, we soon should have the dates for examinations and deadlines. Okay, when you see something in Slack and it has been pinned, then you read that, because everything that is pinned, I assume that you have read. So there might be quick changes, like, if my kids are sick or something like that, and then I need to stay home, I'm writing it on Slack before, as early as possible, right? There might be changes in assignment, there might be new things in the schedule or rearrangements in the schedule. I'm putting all that in Slack as pin posts, and everything that is pin post, you need to read that. So think of that as something that is a must read. When you've read it, you add a reaction to it. Could be a thumbs up, could be a thumbs down, could be a smiley face, or one of these annoying animated emojis. Yes, this is important for me, because then I know that you've partaken in that information. Okay, so we have a number of goals in this course. The first goal is that you, on your own, automate testing techniques. So you should be able to individually implement testing techniques. And we examine that through 2 assignments. The assignment 1, part 1, part 2, and then assignment 2. Both of these includes automated testing techniques. Plan, document, conduct testing of a software, assignment 2. So in assignment 2, you're going to choose in groups, in small groups, choose an open source project that you find perhaps on GitHub. And then you're going to analyze that project's testing. And then you're going to improve that project's testing also. So that is assignment 2. So we're going to look at real-world testing projects. The third one, critically evaluate software testing literatures, assignment 3. So in this assignment, you're going to find and read a scientific article or paper on testing. So you're going to find some cool on the edge testing technique, perhaps, or some research on testing. And present in-depth testing research, assignment 3. So assignment 3 is going to be presented in small groups after New Year's also. Explain basic terms and principle. Assignment 2, assignment 3, and also the exam. So this lecture today, this lecture Basics of Testing, has a lot of different terms and a lot of different principles and stuff like that. So the lecture contents are going to be examined during the exam and in the end of the course. Explain the role of testing in software development. Almost all assignments, perhaps not A3, because you select a scientific paper on testing in A3, and it might contain anything that is, so I don't know, but it could be that. So we should cover all the goals through the assignments. So the first assignment, part 1, is that you're going to learn unit testing with PHP. So PHP is a programming language for the web. It's mainly, or it's solely server programming. And I don't assume that any of you have read PHP before. It's a quite easy to learn, quick language to learn, and the assignment itself contains the information that you need to learn in order to be able to program it. So we're going to do, it's fully automated also. So you're, going to work in a tool called CS Quiz that I've written. It's a bit old right now, but you should be able to still program in it. It's mandatory, so everyone needs to do this assignment, even if you're going for higher grade. So when you've done that assignment, you should know the basic concepts of writing unit tests. And you've done it in PHP, but the basic concepts is, language agnostic. So it doesn't matter which language you have. So PHP, it's just another language. If you're a web programmer, at least you should know some PHP when you've done your programming educations. So here you get it. Then assignment 1, part 2, a TDD project. This is going to be a test-driven development project. Hence, the test-driven development book is good for this one, right? It's optional for higher grades. So if you want a D or higher, D to A, you need to also do this. If you passed assignment 1, part 1, you cannot really fail on part 2. So you still will get an E grade if you passed PHP CS Quiz. Then the assignment 2 is about testing an entire software, system testing. So you're going to write the test plan, test cases, and test report for system. We're going to work with open source system. And in some cases, these open source systems provide a lot of information. In other cases, you're going to need to, be a bit of a private investigator or a detective in order to. But you're going to take an open source project, you're going to start it up, you're going to run it, you're going to test it, you're going to try to find its requirements and see how they are tested. That is going to be presented during a workshop in January. And then A3, read a peer-reviewed scientific paper. That is also going to be presented during a workshop in January. And then the exam covers the book and lectures. Yeah, we've already talked about the 2 books. But there are a lot of these, and we've also seen these video lectures and stuff on the course web. Yeah. So these are the study guides. We've also covered that already. And then we have CS Quiz. So on the right-hand corner, you can see a screenshot from CS Quiz. So it's an integrated development and very simplistic integrated development environment in the browser. So you're programming in the browser, you're also getting all the instructions in the browser, and you also get the compilation and everything. So it's not a compile, it's in interpret language. So you get, these are test cases on the right hand that you need to pass in order to pass an assignment. And then in the bottom, you get the output from the error messages. And you can also see the output that would be in the browser by clicking output here. You can click on the different files and get their contents. I'm sure you're going to feel a bit annoyed by the simplistic editor, right? Because you're going to work in the browser. But still, this is a very simple way for me to provide this assignment to 95 students. And when you passed it, you got an E grade on assignment 1, part 1, right? the different parts is the first part is that you need to learn a little bit about the tool itself, CS Quiz, and also PHP in order to pass this assignment. So you do the red tasks in order to know a little bit about PHP. And then you have some practice tasks on unit testing and some lectures on unit testing. So you do those in order to learn the testing framework within this tool. And also you learn how to write automated unit tests. And then you also learn a little bit about these different testing problems or situations where you are supposed to be able to write automated unit tests for. And then finally, there are some examination tasks. Good to know is that these examination tasks, even if you are provided them directly, most students need to do the exercises. Unless you already know PHP a lot and you have a good amount of practice on writing automated unit tests, you still need to do some of the practice tasks, right? It's not actually written to be hard. It's just that you need to get used to the tool. I think that is going to be the biggest obstacle for most of you. If you're aiming not to learn, that could also be an obstacle. So I've seen some students that are, just skipping through the easy exercises without really trying to learn anything about it. And then they have a big problem with the examination task. So go through these exercises. Every exercise is, created in order for you to be able to step towards the goal of passing the examination, right? And you can, redo this a lot of times also. So you can reset the files and do the same thing over and again. Yeah. A rough planning of the course week-wise is like this. So this week we have course introduction and basic of testing. You're reading some parts of the book, and then you're starting with the assignment 1, part 1. And you can see that the deadline for assignment 1, part 1 is in 2 weeks, so week 47. And assignment 1, part 2 starts next week. So this, you could actually start it this week also. So if you're aiming for a higher grade, this is just to show you that I want those that want a higher grade to speed up a little bit, right? And then assignment 2, in order to start that one, we need a bit more of the lectures in order to do that. You could, form groups, choose a project, and start it already because the instructions are out there. I don't expect big changes to the instructions for any of the assignments right now. But it formally starts week 48. So I'm going to give you more information on that, in the lectures that week. And then assignment 3 starts a week later than that. We also have these problematic weeks during Christmas, where people are doing stuff outside of computer science, like meeting people, family, and stuff like that. So in order to let people do that and also let me to do that, we have this repetition of the course literature, and we also have working with assignment 2 and assignment 3. So my suggestion is that you try to do the core part of both assignments before Christmas. And the core part of assignment 3 is to choose an article, to find the article that you're going to read, and then, maybe you skim read that before Christmas. And then if you've been working with your group before Christmas, then you can, relax a little bit during Christmas, and you don't need to have group sessions, perhaps online group sessions. And then you reconvene after New Year's, or, maybe a day before, and then you just finish things up for the presentation and stuff like that. This is a bit problematic if you're planning to, I'm going to go 3 weeks to some place with my family and not be able to study. So if you're planning to do that, you need to study ahead. The tutoring sessions is all before Christmas and none after Christmas. So I think the workshops here is for the 4th of January, if I don't misremember. There is a plan of reading the book up until chapter 19 before Christmas, and then you just repeat it before the exam. Sounds reasonable? I hope so. There are a lot of, these guest lectures and stuff like that. So you're going to be busy, but there are these study plans so you can follow. Okay, so if you have trouble registering, write in Slack, state your case, include all information that I need. So questions, and they are recorded now, so you can write your questions in Slack or here in the classroom. Everything crystal clear? Cool. Okay. So we're gonna proceed to the basics of testing. Okay, so this is the first lecture of the course, Basics of Testing. This lecture contains a lot of different terms. So I do understand if you lose track after a while, but we need a common language in order to be able to talk testing together. And in order to have a common language, we need to know the words and sentences of that language. So this lecture is supposed to give you that, right? So get a vocabulary, lots of different definitions, and many of these definitions is also directly for the exam. So re-listen to this one before the exam. Right? Okay, so we start with what is testing, and then we go through a lot of these. So first, a motivating case. So this is one of the computer games that I wrote 2004, I think, something like that. We started with this one. So this is a breakout clone or an Arkanoid clone. So you control this little figure down here, which is your pad, and then you have this ball that is bouncing against blocks over here. And when the ball bounces against the block loses hit points. If it doesn't have any hit points left, then it breaks, right? And your goal is to break the entire level, all blocks. And me and Tobias did a breakout clone that we called Time Breaker, because you were traveling through time, breaking bricks. And then you're getting power-ups. So down here, you can see that things are falling down. So here we have these exploding balls. And whenever they hit a brick, then it's exploding and destroying even more bricks. We did our idea was to be able to have animated 3D levels, but really they are 2D. So the ball is bouncing against the edges of a 3D object that is projected onto the screen, right? So and then these levels were animated. So these were spinning, the truck was spinning and stuff like that. And then you get scores and high scores, and you have lives and all these things. The problem was that we pretty early got a version that worked, right? And we actually called it spheroid in the beginning because we thought that it would be cool to not have a flat pad down here, but that it would be a sphere, so you could, by predicting how it would bounce against the sphere, you would provide the user more control. That was a bad idea, and everybody hated that. So we changed it into this cute little robo guy instead. Problem was that I bought a laptop, and I bought that laptop in order to try out a graphics card that we didn't have access to. And this was an Intel integrated graphics card. So this was exactly the time where the the CPU manufacturers like Intel started to produce graphics card integrated in their processors or integrated into the main boards of the computers. And I started up the game and everything ran some of the time. But then a lot of the times, perhaps 50% of the time, this happened. So this is the infamous blue screen of death. This means that the operating system Windows crashed completely. So this was a showstopper because I think the market analysis was something like 15% to 30% of the market of these kind of simple downloadable games, shareware games they were called, would have these kinds of graphics card. And when you get one of these crashes, then the operating system is completely halted. So everything you have not saved was lost. So we imagine ourselves getting sued by angry Americans on the international market. So we need to find the bug, really. So I started to hunt for this bug because I had the only computer that was available that we could reproduce the bug on. And the error message here really does not tell us more than that it stopped. We could see that this is some kind of driver issue. So I contacted Intel. I worked with their engineers for a while. I, just tried to start the program in a debug mode and see if it crashed. So I started this game in the debug mode, and it never crashed in debug mode. So I could never find the spot where it crashed, where the bug was. And then I started to, break down the program into smaller parts. So I removed half of the code. It's still unplayable. And then see if it crashed in the first part of the code. And sometimes it did, sometimes it didn't. So this was, a bug where that didn't always crash. Sometimes it crashed early, sometimes it crashed late. So every time I did a change in order to debug something, I needed to restart the game and play it for a number of times in order to guess that the code did contain the bug or not. So this took me 6 months to do this. And the thing is that during these 6 months, we were, trying to be a startup, a game development company, and trying to push our first product out. And we were working with a producer that had goals for us, right? We were working with Alavar Entertainment, an American company, and we had pressure on ourselves. So I was working with it. It was actually quite tough mentally to work with this, because sometimes when the computer crashed, then I need to restart, not only restart it, I need to reinstall Windows after this, because Windows broke some of the times. And then finally, I learned a little bit with the Intel engineers about something called lazy loading. And then I fixed the bug, and the bug was gone after 6 months. And I think it was like 2 weeks after fixing the bug that I was browsing through the code of Quake-free. So ID Software just released the Quake-free code, source code to the game Quake-free. And I find this line. This is the solution to the bug. And yeah, so 2 weeks after spending 6 months, I find the solution. So the bug was that when you're loading textures, that is images, into the GPU, in this graphics card, they were not really loaded. So if you had too many textures that you tried to load into the graphics card, but they were not really loaded when they should be loaded, but they were loaded when they were used. So if you try to use a lot of textures that were not loaded into the graphics card, and then you use all of them at the same time, and then it tries to load all of them very fast, and then it crashed. So the workaround was really to load one texture, then use it. So I actually plotted 1 pixel with this texture, and then load the next texture and use it, and so that all textures were loaded into the graphics card memory. Yeah. So I got a question on A3 also. A3 is individual. So A1 individual, and A1 part 1 individual, A1 part 2 in pairs, could be done individual in pairs, A2 in groups, A3 individual. Okay, so what is testing? Testing is to show that a program does what it is intended to do, and to discover defects, preferably before it is put into use. So I needed to find this bug before we could release the game, right? Show that the program does what is intended to do. What is intended to do is actually requirements or specification of the program. The requirements specifies an expected behavior. So this is the way the game should work. It should not crash. It should not produce blue screens, right? It should be fun, for instance, could be one part of it. The requirements could be like things like the ball should bounce on the edge of the screen, or a brick should break if it has no hit points and stuff like that. Show that the program does means that in order to test the program, we need to run the program to get the actual behavior. So we have expected behavior, and then we have actual behavior. And show that the program does also means that we run the program, which is a dynamic activity. So there are static activities that we can look. We can, for instance, look at source code, and we can say that this code would never work. So if we're just looking at the code and not running the program, then we're working statically. If we're running the program, then we're working dynamically. Yeah, and then we discover defects, right? So we compare the actual behavior to the expected behavior. And if these match, then we do not have a bug. If they do not match, then we have a bug, right? So a test case is specific input and expected output for certain system. How should it work with these inputs? So when we have testing, then we can check conformance of a system to its requirements. Sometimes I'm going to call the requirements or the collection of requirements a specification. So if I'm comparing the requirements and the system, and with the system I mean everything that we are programming. So it could also be, configuring servers. It could be all the parts of the program, right? We call this verification of the system. So when we compare, when we do that, we build confidence in the software. So before I discovered what the reason was for our crash bug, I did not have confidence in releasing the system, right? And if the customer were to play my game and it blue screened, then they would not have confidence in the system, right? So when we remove the bugs, everyone gains confidence, both developers and customers. We also want to uncover problems, defects, and bugs in the implemented system. We also want to understand the implemented system. So we write code statically. We're writing text most of the time. I mean, there are some graphic programming language where we, can drag and drop, and we automatically generate code today also. But we need to understand, how does this work? What is the effect of these instructions? But we also want to know what of all of these requirements, what has been implemented yet? What does work? What does not work yet? So we want to understand the implemented system, but this specification itself is not a complete thing. It also contains like holes, things that we have not thought of. So for instance, what happens if the user does like this? So in the browser, they're using our application, and perhaps they, press the back button twice or something like that. And then they go back to a page that was, we perhaps did not expect them to work like that. Perhaps we were only expecting them to click on links or, writing stuff in the application, never go back. Perhaps they changed the URL of our web application. Perhaps they, click just outside of the game area or something like that. What happens? What happens if the user is alt-tabbing from the game out to Windows again and then go back? What happens if we run out of memory? Stuff like that. What happens if the user does this? We learn about the dynamic properties of the system by testing it. So this gives us a deeper understanding of the system, but also how the requirements, but also the requirements themselves. So when we write a specification or requirements, we have some idea on how it will work. So we had the idea of a spherical pad. Oh, that would be so cool. And then Dennis from Alavar, the publisher that we work with, said that this game sucks. So we learned by him testing the game, we learned things about the requirements and if they fulfill the customer's needs. So they did not fulfill Dennis' needs for having fun in the game because he thought it was too hard to always bounce on the round pad. We call this validation. So we have verification and validations. And these are two important concepts. So the first one, validation. Are we building the right product? This means that we have some goals and expectations and needs from the customers. And we try to see, do we fulfill these goals? Is this a good product for these customers to fulfill their goals? Do we solve their problem? Do we entertain the customers, or do we, do we do good in this world? Really, this validation has a high level focus on needs and expectation, and this most probably needs to be done together with the customer, or we as developer need to understand the customer situation in order to do this. Have you ever been, frustrated by a software when you're working with it and it's so hard to get what you want from the software? It should be possible, but it's so hard. And perhaps you get into these very tedious modes of inputting stuff very tediously, and then it should be so good if I just could do this. I just need a button for this, or I need to paste all my data at once into this product instead of inputting one thing at a time. So when we're doing that, we are actually working on the expectations and needs of the customer. So this is validation. When we think about the requirements, do we really get what we want? Then it's validation. Validation testing itself is usually done together with the customer. So they want to say that this is a good program or not. That could be done by having one test per requirement. So if you have 10 requirements, you have 10 tests. And the customer perhaps does do these tests, run these tests themselves. So these could be manual tests. They could absolutely be automated also. So the customer runs these and think, oh yeah, I get what I want. They can see that they get what they want. Such a collection of tests we sometimes call an acceptance test, which means that the customer who is paying for the product is accepting the product. This is the product I want. I can pay for this. Sometimes this acceptance test is, something that is a project requirement, that on this date we must pass the acceptance tests. So we have the cloud here, which is the needs and expectations of the customer. And then we have the box here, which is the implementation. And with implementation, I mean the system, everything that we've written and the working version of the system. And if they completely overlap, if the blue box is covering the cloud altogether, then all the customer's needs are fulfilled by the system. They might not, and often do not, fully overlap. And this is partly because the needs and expectations are fuzzy. They are a cloud. We cannot really grip this. It's not easy to exactly specify what makes a game fun. There are so many not fun computer games out there. Some of them I stopped playing before it has even started. So these annoying intro videos that you're supposed to view when I just want to shoot something now. I don't want to watch a video. I'm not, and this needs and expectations are different also for different people, and they have different goals. They have different problems. So validation, is this good enough? We are working with a specification. We need to communicate with the customer in order to understand this. Then we have verification. Are we building the product right? This is when we have a specification We check that the software meets its stated functional and non-functional requirements. So we try to find faults in the code by finding some input for which the behavior of the system is incorrect. So we're actually looking for bugs. We want to know, we have now, in validation, we try to find out the needs of the customer. So we're much closer to the requirements themselves here. Here we have the requirements. We try to see, okay, does it work like the requirements do? And the question we ask, does this program, A, implement the requirement R correctly? We try to find out, does it work, right? So here we might be very much closer to the code also. We are, talking about different buttons, click these different buttons and stuff like that instead of the needs of the requirement. There is a term, if you're, if you are searching for verification, there's a term called program verification. I just want to warn you, there are different vocabularies out there. And during this course and in the book, and my vocabulary here in the lectures is the one that we need to use in order to be able to communicate successfully. There's something called program verification, which is a model-driven, formal mathematical way of proving that a program works. So we're, using math in order to prove that the implementation works as specified. This is not what we're talking about when we're talking about testing. We are empirically trying different inputs and see if the system works for these specific inputs when we're doing testing. We're not proving anything. There is enough that there exists one input that causes the program to fail for it to have a bug, right? And this could be a very improbable input. We're going to talk about exhaustive testing later. So, okay. So here we have verification. So on the left-hand side, we have this happy dude, and this is a programmer, and he or she has an idea. This is an idea of something. Orange rectangle and a green circle. And they should, overlap a little bit. It should be connected to the right-hand corner. And then this program writes a specification for this one. Orange rectangle, 3, 2.5. Green circle, radius 1.1 is drawn on top. This is what the program is writing. Another programmer, or perhaps the same one, but another day, when the memory of this, this idea of these needs and expectations are no longer present in the brain, or this is a new brain, and they read this specification. They read the specification and interprets it like this. So the green circle is on top. So here we have an error in the mind of the developer that will cause a bug, right? Then the programmer on the right-hand side does an implementation. And this implementation causes the orange box to be drawn, and then the green circle is behind this one. So even if they had this idea, this is the result. So you have had cases where you have been programming and you had a clear idea on what you want, but you didn't get what you want, right? You got something else. Perhaps an error message, or, you get some part of this CSS is wrong and one cannot read the text or something like that. So we do an error here. So we had this error of interpreting the requirements. First, we had the error of not being able to write the requirements so specified so that it cannot be misinterpreted. Then we had a misinterpretation of the requirements, and then we had a misimplementation of this one. Okay, so now we have the left-hand side, the tester, And the tester is writing a test case. So we run this program and we expect the rectangle to be this exact orange color. So 255, 153, and 0 as RGB values, right? Depends on how we test, because actually this color here and this color is not exactly the same, right? That they're not exactly the same. So this tester was reading the specification and interpreting that and say that, oh, I'm going to check the. And this test case does not find any of the other bugs. So we have a specification and we have an implementation, and they overlap. If it's a good implementation, they overlap. So we have implemented stuff that is in the specification. So the green part is the overlap of these two areas. And then we could have things in the specification that we have not yet implemented. So for instance, in the game, we could have ideas for, you know, a boss fight in the brick breaking game in Timebreaker, but we never did a boss fight. We just have, you know, a cool level in the end, but there was no boss. It was not shooting back or something like that. But perhaps we had an idea of that and we wrote that in the specification. So things we have not yet implemented in the implementation, we call those omissions. And you can have something called fault of omission, which means that we have not yet implemented this. Then we have things that we have implemented that was in the specification, but we did not get it right. We call those faults or bugs. It's not, yeah, so faults of omissions are things outside of the implementation. We have not yet done those. And then we have faults inside the implementation. There can be many reasons for this. We talked about a couple of reasons, the you know, imperfect specification, imperfect interpretation of the specification, imperfect implementation, imperfect test cases. But we find faults. And then we also have stuff in the implementation that we did not think about when we did the specification. So perhaps so we call those surprises. So an Easter egg in a program is a typical. I watched a lecture by this really fun programming guy, and you know, he had this really cool software for painting textures inside games, but in like Photoshop. So you were painting in Photoshop, and then it automatically saved the texture, and you could see the result in the game running at the same time. And a part of his software that he wrote a dialogue, you could like click in on a specific pixel, and then it started the mini game in this. I'm sure the mini game itself was not in the specification for this. It was just something that he produced for his own amusement, right? So we can have things in the implementation. Normally, when we're talking about verification, we do not call bugs in the implementation that was not in the specification for bugs. They're just annoyances. They're just outside of the things, because the verification part is to check the code that is overlapping with the specification and the implementation. Okay, a lot of different terms already, and I think that we should have a short break. So let's take 10 minutes break. 10:20 we start again. Okay, so we had specification, implementation, and the overlap. The part that is overlapping that is working as specified, then that is the correct code. Then we have the code with the bugs in it, and that must be within the overlap. You could have faults of omission, but faults of omission is a part of the specification that you have not yet implemented. And then you could have something in the outside of the specification that it's also not working as it should be, but then we really don't know what that is. I mean, if it's breaking the entire system, then of course, then it's a bug, right? So if it's hampering our ability to work with the goals that we have, then of course it's a bug also. But if it's outside the specification, then we call it surprise instead, right? So specifications are always interpreted. I mean, there are these, very formal specifications that are really hard to read and really hard to work with, but usually we try to communicate with each other instead. What do we want? What does the customer want? And then we try to, write that down in a format that the customer also understands, and then we interpret that in order to do a system. So testing is super important in order to find out more about the system, implemented system. So there are two concepts here, and sometimes they are used overlapping, and often we are using testing for both of these. But I want to introduce checking. So testing is when you are coming up with a test. So it's a creative process. What and why should we test? So I want to test, for instance, the front end. I want to test what happens to the form in the browser when I do this. So we have some testing goals, for instance, that we want to cover some requirements or we want to cover some code. We decide what part of the system do we test. We call that the system under test, or SUT. What inputs are we going to use? What is the situation? What are we going to click before this? What are we going to write? How do we stimulate the system before using it? And then we also try to find out what is the expected behavior. So that is usually what we call testing, right? And then checking is when we run a test and check the output. So if you are writing down a test, like a manual test case, or if you're writing an automated unit test, then you're only doing testing once. And then you check the test many times, perhaps. So checking, if you're manually testing, then you enter the input, but you could script this also. And then you check the output, and then you compare the checked output with the expected. You compare the actual with the expected. So checking, many say that testing is boring. And I would say like this: checking is boring. Testing itself is a creative process. How am I going to break this system? What kind of input am I going to do? What do we need to test? Which requirements are tested? What are the expected behaviors of these different components? All of those are not boring, I would say. These are just, things we do as programmers. Checking itself can be boring. The first time we check something, it's not boring, because then I like to find out. You just written a test case and you input the stuff, and then you compare these, and then you find out, you get information back. But the second time, if you're doing manually, then it becomes repetitive, and that could be boring, unless you like repetitive tasks. I can be quite good at them, just to focus on one thing, and then I do this, and then I usually reward myself with something afterwards, candy or something like that, right? But if you're bored, as a programmer, if you're bored, then you should do something about that. So your boredom, your feeling of boredom, is a hint that you should automate more. The more we automate, then the checking part can be automated completely in almost every case. We might still need to do testing with checking on a product, because like for the computer games, even if I did some automated testing that was actually running the game, then we also need to find out, is it fun or not? And that is hard to do automatically, because fun is such a fuzzy, what a computer finds fun is not the same thing that I find fun. Okay, conclusion. Testing is to come up with ways to run the system, exercise the system dynamically, which means that the system is run, with the aim of finding faults. So testing is dynamic. Checking enters input, compares expected behavior and actual behavior, and validation is more goal-oriented testing. So we are thinking about the goals of the customer, and verification is to check, is the testing and the specification, are we doing it right? Conformance to requirements. Okay, so that was the first part of this, and now we continue with more things. Faults, error state, failure, infections, propagation, and testability. So let's first look at the first bug. So this is an actual moth, and mal på svenska, moth. And this moth was the first bug. That's why it's called bugs. So the first bug was a bug. So in the beginning, the first computers had electronical relay, which is a magnetic switch. So an open switch is a 0, and a closed switch is a 1. Think of this as a button, more or less. And the first computers had a lot of these, and they were actually clicking when they were running, like tick, 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 tick. So the first computers did sound a lot. But if you get a bug that is landing on the pad that is supposed to be connected, and it fails the energy to be conducted through the bug, then we have a bug. Right? So the first bug was a bug. Okay, but what we usually mean when we are talking about bugs is a defect or a fault. So these three words can be used overlapping: faults, defects, and bugs. This is a static flaw in a program. It's something in your code that needs to be changed, something that you can do. It could actually be also a bug in the state of the code. So in your database, in an environment variable, in some persisted file or something like that, that causes it. Actually, the state part, we're going to talk about error state. So usually we just mean code changes when we're talking about bugs. But sometimes when we're talking about bugs, it could also be that, oh, this user did not have a password in the database for some reason. Okay, so let's look at this code down here. Do you see the bug? It's an add A and B, but it does not add things. A and B. So it should have a plus sign instead of a minus sign. Okay, this not very hard to find, right? Because it's very easy when it's such small code. But this means that we need to change this minus sign into a plus sign. Okay. Let's assume that code now, that we have this bug. Okay, we have something called state. A state is the dynamic content in variables and storage that can change in a program. So for instance, we have this variable A, and we assign it to a 3. Now, somewhere in the memory of the computer, in the memory of this program, there is a position in the memory with an integer 3 in it, right? This is the state. All variables of the entire program that is alive right now is the program state. So if everything is okay, then we are in a good program state. If some of these are not in the correct value, then we are in an error state. So let's think about this. We call the add method 3, 4. We send it a 3 and a 4. That means 3 and a 4. 3 minus 4 becomes minus 1. Now, the variable sum is in an error state. It has the wrong value. It should be 7, but it's minus 1. It got infected by a bug in add. So when we have a bug, when we have something, a fault in our program, some line of code that should be changed, it puts the entire program in an error state. Now some variables are changed in a way that, or this could be saved into a database also. It could be saved into a file. It could be saved into local storage or something like that. Now we're in error state. Sometimes we run code with inputs that does not put us, we run faults with inputs that does not produce an error. So let's assume that we send it a 3 and a 0. 3, 0. 3 minus 0 is the same thing as 3 plus 0, right? So even if the bug was exercised, even if it was run dynamically, sum is still okay. And this is the difficult thing here. This is the thing that makes finding bugs difficult. And sometimes it's not easy to see that the bug or that the program is in an error state. So think about this one. So we look at this orange color here. We compare it to the other orange color, and we say that, yeah, these looks the same, but really they're not. Okay. So in order to find a fault with a test, a number of things needs to happen. We need to reach the location of the fault in the source code. So we need to run the add method. If we cannot run the add method, it will not produce an error state, and then we will not find the bug. So the faulty method add must be executed. And then an infection must happen. The fault must alter the program state into a bad or error state, into the legal state. So we need to have a non-zero B for this to happen. Since B needs to be a non-zero, it could be a negative number, it could be a positive number, but it cannot be 0. And then finally, not finally actually, that the error must be propagated in a way that it produces output so that we can look at that output. So if the sum is never used, if it's just, returning there after that line, if it's just, returning after this line, sum is just thrown away, then we won't discover the bug. So in order to find the bug, the error state must propagate to the surface where we can observe it. And we call that, we produce an incorrect output that is called an observable failure. You must show that the output of add to the user. So an observable incorrect behavior of a program as a result of an error state. So a failure is when we reach the surface somehow. So sometimes there can be very long time between a fault or an infection. A fault causes an infection until it propagates to the surface again. So think of this: we do a bank transaction, and somewhere in the bank transaction, you're paying at ICA or something like that with your card, and then the wrong value is withdrawn. Now that is put into the bank's database, right? And no one is looking at that value anymore until you open your bank and you look at the amount that you have on your card, and you see something, or you don't see something. But a failure is an observable incorrect behavior. So you see that the sum is wrong, or you could see that the sum is wrong. Not every error state ever surfaces to an output. So there are many databases out there with error states in them. And not every failure is observed. So if I were looking at my bank account and it was just 2 kronas more or 2 kronas less, I would not observe that. If it's 1,000 kronas, I might observe it, right? If it's 10,000 kronas, I'm definitely going to observe it. Where did my money go? Right? If it's to öre, I would never observe it, right? So some things are hard to observe, like these two orange colors. Even if we could observe that there are different colors here. So yeah, in testing, we want to observe failures. We want to know if there is a failure. So we have different kinds of goals. Controllability, the first one. We need to run the program. We need to run the program with the fault, the part of the program with the fault, right? So we need to steer the program to a point that we want to test. I want to test the add method now. So we need to reach that fault, run the code with the bug. We need to produce an error state, and we need to make the error visible as a failure. So if I cannot run the add method, if it's very deep, like in the code, and I always, if I always start the program through void main or something like that, and I never can run a single method, it's by itself. Like in my computer games, I had the case where, the bug occurred in level 3, right? That is hard to run that code that only runs in level 3 when that enemy or something like that is put onto the screen. At that point first. So in order to reach the fault, I need to play through level 1, 2, and 3 in order to get there, right? So that meant that I had low controllability. I can increase the controllability by introducing ways of running code. So for instance, in the computer games, it's very common to have sheets. So you input the code, or you can just jump through the levels as testers. I can jump directly to level 3, and maybe I can jump directly to the final boss or something like that on level 3. Yeah. If you have automated unit tests, you run a single method. That is increasing the controllability a lot. That is why we love our unit tests, because we have high controllability. We want to be able to produce an error state. That means that we want to send specific inputs. So we had the case with the add method, right? And in this case, the only value that does not produce an error state was 0. But there might be the opposite around. There might be only one input that produces the error state, and all the others are producing correct output. This is quite common, actually. Oh, if these 3 variables are in the exact numbers, then we get to an error state. But other than that, we don't observe it. So they can be different, hard to. And then we need to make the error visible as a failure. That was not very easy with these orange colors. But if I have an assert, and I assert these RGB values, or an if statement between these RGB values, it's easy to see that they are different. Okay. Then observability. So first was controllability. We should be able to observe it, right? Then we have observability. We need to see what the application is doing. So if everything is put into a database and I never see the values, I cannot get a failure. If I am writing automated unit tests and they have an assert in them and they compare 2 variables, then it's easy. This is a problem with observability between these 2 rectangles. So if I have these 2 things together, controllability plus observability, then I have testability. Yeah. Usually, we also need specification and requirements in order to understand what to test and detect failures. So we need to understand the system. If you don't understand the system, what it's supposed to do, then you can, if you're just imagining a specification, then anything can be wrong and everything can be right. So you need some idea. And the specification is actually, and you probably will realize this when you're, working with assignment 2, is that it could be very unclear. It could either be a lot of different information that you need to sit down with, or it could be very sparse. Many cases when you have been writing programs, you have been writing sparse specifications because you don't want to spend too much time with writing requirements. You want to get into the code now. I would like to get into the code now. There are actually ways of writing executable specifications where we can get specifications as code. Okay, more goals of test cases. Accuracy. The first one is that how can we isolate the faulty code? If I run only the add method in a unit test, then it's very easy to say that, okay, this unit test broke, and if the fault of that must be in the add method. Sometimes we cannot run just one part of the code because we have created components. Perhaps add method is a private method, so we cannot run it. Perhaps we want to, in order to run the add method, it can only be run through another method, a public method in this class or something like that. Suddenly we have more code. The more code I run, for instance, when I was looking for the bug or the blue screen of death bug that I talked about, I ran the entire system. I ran the entire program, all 10,000 lines of code. And I didn't know which one had a problem. So I had a problem with accuracy with my testing, right? Could not run separate parts. So I had, but if I could run the exact part of the code that produced the bug, then that would be a high accuracy. Sometimes bugs are not as easy as the add method. The bug is only happening when some part of the code is run, then another part of the code is run, and then the third part of the code is run. So we need to change all 3 parts in order to remove the bug. Yeah. Okay, traceability. So that is, we need to, in order to communicate to someone what to do. Now we have found a fault. Now we need to do something about it. We need to connect the failing test case to a piece of code. So which code is tested? So traceability is also a good thing with automated unit tests, because if we're running just a small part of the code, perhaps we're naming the unit test in such a way that it's easy to know which method was tested, then it's easy to find the code. But the other thing is to know which failing test case is connected to which requirement. Then we need to know how are requirements and tests connected. That is usually done during a matrix, and we're going to look into that in the system testing code. Chris writes, colors are displayed differently on different screens. How do you handle such cases, given that the RGB values are the same, but the colors differ when compared side by side? Yeah, so I think this is a good question. How do we observe things when our screens are different? So actually, when we moved to these flat screens, I actually kept a CRT monitor, one of these fat screens, because they were, in the beginning, they were better at producing colors. So we wanted to know that our game could run on both. We want to know how they looked on both of these screens. So if you're working with a lot of different hardware, you actually need that hardware in order to be able to test it. But knowing, how it would look at home of your users, how it will look there, of course, it's impossible. But yeah, when you're doing, programming for mobile phones and stuff like that, yeah, you probably need a number of, hardwares in order to test that things in a reasonable manner, right? Okay, so conclusion here is a fault is a static bug that can lead to an error state if it's executed, if we reached it. This was called reachability, right? We need to reach the part of the code. The fault itself infects the state that is changed into an illegal one, an error state. For the error state to be detected, it must surface to the output and be observable. We call that a failure. An observable failure, and then an observed failure. Finally, we as testers must observe it. We need to look at this, and then we must make a judgment that it's not what we expected. So I can look at the sum of my bank account, and I can come up with the conclusion, this looks okay, when it's really an error state. I can still make a judgment, a wrong judgment. Okay. A lot of these different terms, right? Now you realize I need to repeat this one. So we continue with a test case. Here is a little bit of PHP code. Let's see it as a preparation for A1, part 1. So we have the system under test in PHP. So these dollar signs tell us this is a variable, argument, 2 arguments, and then we have the minus sign here, right? Then we have a test case. So we have the first input 3, the second input 2, then we have the expected value 5. We exercise the system under test, which is that we run the method that we want to test with the input, and then we get an actual value back. Then we compare the actual to the expected value. If these are the same, we say that it works. Okay, so a test case in JavaScript could look like this. So we describe, this is the name of the test case. And then it has, I've just copied this. I don't think that we really need to read, but it can look, this is from Java. So a test framework from Java. I think the first one is Jest. I'm not sure, but I think it's Jest. And then we have JUnit 4, I'm guessing. So here we expect an exception to be thrown when I send a from string with this empty. And then here we have a C# test case. So these can look a little bit different. So we have these different frameworks for testing. Usually, I still, even if they look a bit different, I want to see these different parts: the input, the expected value, the actual, and the comparison in these. Okay, so if you look at these different components in this, is that we have a system under test. This is the thing that I'm testing. I actually call it always system under test, even if it's like a method under test, class under test, object under test, component under test. I always call it system under test. System under test means what we are testing. The smaller the system under test is, the better accuracy we have, right? The larger it is, it's harder to find where the fault is. Okay, system under test is the thing we're testing. I always call it SUT, the executable class method that we try. For, in our case, the add method. Then we have explicit input. This means that it's not fuzzy input. That means that we have values for the input. We had a 3 and a 4. It's not put numbers. How to handle the SUT before checking input. Then we have the expected output behavior. We expect this SUT to output before the expected value. And then we have the actual behavior. In order to get the actual behavior, we need to exercise the system under test so that we get an output. Sometimes the output is not a return value. It's easier to test with return values than with other kinds of things. But it's not always a return value. We're going to talk more about that when we're talking about unit testing. And then finally, observed output or behavior. How we saw the actual output. So the observed here in my little PHP code is an if statement that lets us to observe it works. If it doesn't work, nothing is printed, which is hard. So a unit testing framework usually gives us more clues than that when we say that. Okay, the oracle is the definition of what, or the oracle decides if the observed behavior matches the expected behavior. So we, as humans, are quite good to know how things work together, how things work in, if it solves our problem or not, right? We're going to go back to these ones. I actually don't mind the difference in color here. Does it annoy you that it's a different color? Doesn't matter, right? Probably. For me, it doesn't matter. Depends on the case. We are really, really good as humans to know if it matters or not. Computers, they are very exact, right? They want to do exactly as we say to them. So they might say that these are completely different values now because we have one RGB value wrong. But humans probably would not observe it. So the oracle is the source of truth. When we program it as an if statement or an assert. So we could program an assert or an if statement in such a way that we allow there to be a little bit of difference between these two orange colors. Or we can say that these must be exactly the same. Yeah. So when we write test cases, we are testers. We are the oracle that produce the truth, so to speak. But we can also let a machine do this. Okay, so many of these things are already written. So we have a specification. It's used by a programmer to write code. The code becomes a program. When we write code, we might do an error. We do an error in thought or in action. That leads to a fault. We could interpret the requirements wrongly. We could write the requirements wrongly. We could write the code wrongly. And that error leads to a fault in the program. The program produces actual behavior that leads to observed output behavior. It could lead to observed behavior. The specification itself determines expected output or desired behavior. And then the oracle decides, are these the same or not? If they are the same, yes, this is what we expect. The test case succeeds. If they are not the same, if we determine them to not be the same, we have a failure. Yes. So we want to be able to do checking a lot because we want to be able to write our programs in an agile manner. And agile development, agile software development, develops software incrementally in iterations. So in every iteration, we want to be able to test before releasing it. So that means that we want to be able to run a test and get the result. The next time we're going to run the test, we want to have the same result. So for instance, if I run my game once and it did not fail, I did not get the blue screen of death. And then I run it again and it fails. I get a blue screen of death. I did not change anything. I did not do anything differently. It was just out of chance, right? So this lazy loading bug that I had that caused the crash was not predictable. That means that I could not easily reproduce the error. When I tried to run the program again in debug mode, I tried to reproduce the error in debug mode, but I could not do that. So that was super frustrating, and that prolonged the bug hunt activity to 6 months because this was so hard to reproduce. So reproducibility is really important. So we want tests to run deterministically. We want the same result every time for the same input. So if I write a unit test, so let's imagine that we write a unit test for a die game. So we roll dice 1 to 6, and I say that it should be a 1. As I assert that the output is 1, but really it's random. Then whenever I get a succeeding result and wherever I get a failure, then I cannot be sure that the next time I run my tests that I get the same result because it's random, right? We call such tests flaky tests. So sometimes they cause failure, sometimes they do not. This prolongs the time it takes to debug stuff. And we can get this into this test and fix cycles where it's never ending. So you can imagine that testers say that this does not work. The programmers run it. They say that it works. The testers say that does not work. The programmers run it, say that it works, perhaps due to changes in their environment variables or something like that. So flaky tests. This is a big problem, and we need to be able to control the program state and things that normally vary, like timing, databases, environment variables, versions of our dependencies and stuff like that. And we also need to have explicit input in order for this. If I have non-explicit input, like input any number, and we run the add test, and one tester is inputting a 0 and another is inputting a 1, they come up with different conclusions, right? So by having explicit input, both will come up with the same conclusions that add has a bug in it. We also need to agree on how Oracle decisions are made, right? We need to have the same agreement on what is correct behavior. Yes, and I think that we need 10 minutes break. So we continue 10 minutes past 11. Is there any best practice or software that can simulate this? Simulate hardware, I think there are a lot of different emulators. Test can be close to a value tool. I'm not sure what you mean. Okay. So we continue. So this is a test case from one of my assignments, and this I let the students run this test case. So this is a name of the test case. Test cases usually have some kind of number also in order to, either connect them, traceability, connect them to a requirement. In this case, a requirement 1. Navigate to page, normal navigation to page is shown. And in this test case, we want to know if the date was shown, right? So today dates was shown day of week, day of month as text, year with 4 digits, time is hour, minutes, and seconds, and an example. And this is what you do. You clear existing cookies, you navigate to site, and then what you should look for then, okay? The not logged in should be shown, a form for login is shown, and today's date and time is shown in the correct format. Clear? Do you think that this is clear? So in order to make it even more clear, I introduced the picture below, right? So a picture is quite good because then you can look at the picture and easily get an idea on the expected output. So, okay, so we're not logged in. Yeah, that should be shown. A form, okay, yeah, it should look something like this at least, right? And then today's date and time is shown, and this was 2015, apparently, really long time ago. So this is this clear? Would you expect the results? Could you do this? Do you, if I gave you this, could you check this test case? Checking, run the test case. Yeah. Everyone? No, you don't need to enter anything. Clear existing cookies, navigate to site, look at for the different things. Okay, so this is what a student sent to me. Here, the student found a bug using this one, right? But 60% of the testers, students, thought that this test case was correct. 1 out of 65 students found the above bug. So here, the day of the week should be shown first. Thursday in this case, here it should be Sunday. This student tested this code on a Sunday. And I never done it because I wrote my code during weeks. So there was actually a bug that was not intentional by me. So when it comes to reproducibility, and this is a flaky test because it did not always have the same results. On Sundays, it looked like that didn't produce an output, but on the other days, it produced the correct output. So the flaky test. So we need to be able to control the program state, like timing, databases, random, and stuff like that in order to get it. But the interesting thing was that 40% assumed the test case to be not correct. But only 1 found this bug. This is actually the only bug that I know of, at least. But 40% still thought that they find other bugs. The interesting thing here is that the developers, actually the students, did not read or misread the documentation. Yeah, no, that was actually the reason for me having that bug. But the students thought that that this test case was wrong, or the implementation was wrong according to the test case. And many of the students said that they looked at the picture down here, which is an example output, right? And they say that, oh, it's not 6th of August, it's another date. And then they thought that was wrong. But that is actually an interpretation of the test case that was wrong, right? So the test case could be even more clear, perhaps, say that this is an example output and not just a screenshot and stuff like that. So we can have different reasons for flaky tests. So interpretations of test case might not be very clear. The the easier it is to interpret it, the less text we need to read and stuff like that, reduces the flakiness or the misunderstandings. So I found out when I did this with my student, I found out that almost every test case was like this. There was always some students that thought that the test case failed, while other students thought that the test case succeeded. So time of day, variation of testing condition, of course. In the time of day, you can think of that as input into the application, right? Everything that comes in is input. Timing, sometimes, you know, if I click fast enough, then I can reproduce the bug. Environment, hardware, software, of course, some bugs only appear with some versions of the drivers, like my bug. Only if I have this Intel bug, Intel graphics card with this specific driver, we could reproduce this. It could be order in which the test cases are run. So if you run one test case before the other, then the other will fail. If you doesn't run the first test case before, then it will succeed. So you can have many of these different things. In that case, it's state, right? So you're probably state dependent. So you want to reset state in order to get more deterministic. Ambiguous test cases, language and interpretation of the test cases, how it's written, of course. And then, of course, you can have faulty test cases also. So the error is not in the implementation, it's in the test case. We have written the test case wrongly. Yeah. And I would say like this, failing tests is not a sign of bad programmers, not a sign of bad testers, it's a sign of miscommunication. We are misunderstanding each other. So a lot of testing is about making yourself understand. I learned a lot about this. I mean, this validation of HTML, CSS, 53% of the students said that it fulfills the requirements. 53% said that it does not fulfill their requirements. They actually ran the validator because it did not fulfill. And then 3 students just click, yeah, it fulfilled. I cannot imagine that they ran the validator code on the CSS. Or they did that in, you know, some specific case where it was valid. Okay. So we need more definitions now. And as I warned you, there are a lot of these definitions. And, you know, many of these definitions are actually on the exam also. So I'm just going to repeat that so you stay motivated to listen to me. Okay, let's first talk about input domain. So input domain is the set of all possible input to a program. Sometimes it's called input space, but input domain is the word we're gonna use. So think of add method. The add method had 2 different integers, A and B, as input. So the input space contains different inputs. So we could send a 0 and 0, we could send a 0 and a 1, we could send a 1 and a 0, we can send a 2 and a 1, a 2 and a 0, 2, 1 and 2, and yeah, you know, all these different numbers. Minus 2.1 billion to 2.1 billion for A, and times minus 2.1 billion to 2.5 billion for B, if it's a 32-bit integer number. So all combinations of that is the input space. So, and then we have correctness. A program is considered correct if it behaves as expected on each element of its input domain. So in order to run add method and say that it's correct, we need to run all those test cases, all inputs. We call that exhaustive testing. Usually we cannot do that. We need to select test cases. So instead of correctness, we usually with testing cannot say that the program is correct. If you have very limited input domain, if I'm sending a Boolean, for instance, then, and that is the only thing that it depends on, then you can, you know, have 2 test cases. One for the Boolean being false, one for the Boolean being true, and then we can run all of them. very, very limited programs can be tested for correctness. Usually, we need to instead rely on reliability as a score. And reliability is like this. Reliability of a program is the probability of its successful execution on a randomly selected element of its input domain. So here is, if the input domain is 10 different values in the input domain, we do how many of these 10 inputs would produce a correct behavior? So let's say that only when I send it to 0, the bug appears. If I send it 1 to 9, then the bug does not appear. So the reliability is 90% for that one. But here we usually, yeah. Okay. Exhaustive testing is impossible for most applications. So in this case, it's super easy to find a bug, then minus sign, right? So we only need one test case where B is not 0 in order to find the bug. Still, if we wanted to test every part of the input domain in order to prove correctness, that would be called exhaustive testing. We test every possible combination. But an integer is a 32-bit integers, goes from -2 billions to 2 billions. And then we have another one. And every combination of these leads to 2.2 to the power 32 times 2 to the power 32, which is a huge number. So even with this super simple program, add, we cannot do exhaustive testing. We cannot test every combination. If you have a single string input into your program, then you're not able today to run this on the kind of computers we have today. Maybe quantum computers can solve this with this exhaustive testing for us, but they are not there today. So even this super small problem, we cannot run it on the faster supercomputers because there are too many combinations. So we need to select test cases that have a high probability of finding faults. In this case, super easy. We only need to select a B that is non-zero. Yeah, so I got a question about some of the slides have a reference to a book. Yeah, so this is a book that I have taken these definitions from. Yeah. Okay, so how many test cases can we have? So the first image to the left is from a game that was released 2011 called Age of Conan. And in Age of Conan, sometimes the graphics for the horses were not loaded. So you could have these people that are riding in the air. And then the second video here, not sure that I'm sending sound, it doesn't really matter. This is from the launch of the Ariane 5 rocket. And in this case, it's a multi-billion rocket and very high stakes, a lot of money, very dangerous things they are working with. There were no people on this rocket, at least. But now it's lifting off. Everything is going okay. And then there was this slight programming error that decided that it would be a good thing to do a 90-degree turn in Mach 3 or something like that, Mach 3. So I think it's going to try to do a really, really steep turn. Yeah. There. It's not a good thing. So right that you're programming, right? Well, what is the difference between these two cases? To the left, in Age of Conan, there, I mean, there might be a slight reduce in sales of the game, right? Maybe a couple of $1 million that it costed the gaming company. On the right, this costed billions of dollars and a lot of work. So the test effort for the Ariane rocket should be higher than for a game, because there are higher stakes. The more money, the higher the stakes. So if you have a really high stakes, people involved, people that could die, then you need more testing done, more careful testing. But you cannot test exhaustively for most problems, because we cannot prove correctness with testing. So unless it's very simple cases. This means that the more at stake, the more testing is done. Okay, so finally, we have a number of different levels of testing. So testing can happen on unit level. So unit testing is testing the smallest parts of the program. So we do that when coding. So even before coding in test-driven development, we write the test before we start coding. You're checking a piece of the program, a method, a class, a component, some part, and you decide this is a unit test of this unit, a piece. Integration testing, that is testing how different pieces of your program is working together, how different methods are working together, how different classes are working together, how different components are working together. For instance, you might want to test how your front end is working with your back end. That is integration testing. You might want to see, how does my program work with this new version of the API? That is integration testing. So we are testing how things are working together. Usually, we just try to test the integration part of it, so that we have test units, that they are working correctly independently of each other, and then we have integration tests that checks, this works together. Then we have system testing. Now, even more, or actually, the entire system is tested together. So we test this during system integration. All pieces, for instance, we test the back end and front end together. Backend, front end, and perhaps an API is usually the cases. Backend, front end, API, and database. So you try everything together. The bigger code that we're testing, the less accuracy we have. The harder it is to find the faults or the location of the faults, right? So I was testing the entire game. Because I was doing system testing, it was hard for me to find the fault. Okay, then we have beta testing, which is usually a system test, but with actual users. So we give the system, the full system, to users, and we let them test it as users. So in my case with my games, I let my friends and family play the game, and then I was, watching them, and they were talking about the game. This was fun. This was not fun. This was too hard. This was not too hard. So beta testing is, releasing it. It's today for gaming companies. It's usually not actually testing. Today, beta testing, when they're, releasing the game to a smaller audience before, they are not actually looking for feedback on how their system works. They are actually just promoting their system. Yeah, sometimes they, learn stuff from that. But usually what I've learned is that when they release something to the beta testers, their actual code is so far away from that. It has, surpassed that version. So even if they find problems in the beta test code, they cannot be applied to the new version of the code. Acceptance testing, we've already covered it a little bit, is when we give the system as it should be to the customer, and they accept that system. Usually we do some kind of validation testing so that the users of the system or customers of the system, the ones that ordered the system, can see that they got all the pieces they wanted. So, for instance, they could have a validation test suite where it's one test case per requirement, 1 or 2 test cases per requirement or so. Regression testing is when we rerun the tests again after a change. So in agile software development processes, it's super important to have cheap regression testing. So we are able to check the same test cases over and over again. The faster we can check these test cases, the faster the test cases run, the better, because running the same kind of things manually is boring and error prone. So we regress, we do the same thing again. We do change a little bit piece of the software, perhaps introduce something new, but we regress test all the requirements again, run all the tests again. Okay, now we have a different type. So we had testing levels, and then we have testing types also. So black box testing is a way of thinking when you are writing test cases. When you're thinking black box, you're thinking that I don't know how the code looks inside this black box. So I'm only thinking about the requirements for this black box. So I'm thinking about the expected behavior. So for the add method, let's imagine that we have not seen the code inside the add method. You can think about it. What am I going to send into it? What could be good inputs? What could be the expected values of those inputs? So in this case, we have a black box, the square root function. We input a 9, and we expect the 3 to be 3 out of it. For more complex, square roots, maybe we need a second implementation in order to produce those. So I would sit with my calculator, and then I would, have a square root of 49 or something like that, and then I would, input these values into this. So when we're doing black box testing, we are not thinking about the code inside. We just think about the requirement. What is this black box supposed to do? What kind of problem does it solve? Now, when we are introducing like large language models into our programs, we have no access to the code inside those. So those are black box testing systems. So when we are testing our system together with them, we also need to think about what is the goal, what is the specification of our system, how should it work? So we are going towards more black box systems. There are many systems, even if we have the code, we cannot really think about the code, like other machine learning models where we don't understand the model itself. We might understand a piece of the code that produced the model, or we might understand how the model can produce a result, but we cannot know how the model actually behaves, right? So black box testing. So we are generating from a specification, or we can explore. So what is a good way for this? What should happen when I do this? White box testing, it's also called glass box testing, is when I have code. When I have code, I can make different judgments. I can look at the code and I can say that, for instance, look at the code here. You can see that there are 3 if statements up here, and then I have an if statement, and then I have a try catch. So in order to test all the lines of code in this one, I need to have at least one test case that goes into the first if statement, at least one test case that goes into the second one, at least one that goes into the third one. And then I want to have a couple of test cases going into this one. And then I want to have test cases where this succeed, perhaps this creation of the user. And then I want to have a couple of test cases for the cases where it fails, the different catch. So I could do this. I could think about this since I have the code. If you only get a black box with get user, where you send a user client to it, you might not know all of these cases. So with more information, with how the code works, then it's easier to find specific cases. So testing with knowledge of the code, or with the internal workings of the code, we call that white box or glass box testing. We can generate tests from code. We can give code to a large language model and say that I want to have code that, or I want to have a test case that reaches this if statement here. We also have something called smoke and random testing. So when we have a system like my game, I want to know, how does it have any bug in it? And then I try to run the system in as many ways as possible to see if it crashes. So both smoke and random testing are built that a system can crash. And what a crash is, that it's an observable failure that is easy to determine. So we can decide our program to crash. For instance, that we add in-code asserts, invariants, or defensive programming practices. So we do some input, we run the program, and we hopefully that it crashes. So let's look at smoke testing first. We try to run as large part of the system as possible. I start my game, for instance, and then I look for smoke. And smoke could be, for instance, that we have 100% CPU for a long time. That it never stops, while true loop, perhaps. That is smoke. Smoke could be we don't get any output. So, for instance, you start up your server, you navigate to the site, but you don't get just going to see if I lost. Hopefully, you've not lost a lot of it. I got a network error. I did see that. No. Share screen window. Basics of testing. Yeah. So other smoke could be in code assert. So we could write, a statement inside the program and say that if this happened, then crash. We could find that we run the program and an exception happens. We run the program and we get an error message. We run the program and we get log messages. We run the program and it outputs something that we don't expect, or that we consider an error. So smoke testing is quite good to just get something started and see that, yeah, it can start, it can stop. But smoke testing itself is not very intricate when it comes to checking the output of it. It's not a complete test case where you run a different scenarios and stuff like that. You're just, starting as big part of the system as possible, and then you look for smoke. So, for instance, I wrote a web server, and I just, as a smoke test, I just let a normal unit test start up the server, and then connect to it with a client. A curl call to it. Am I losing stuff here again? Okay, and then we have random testing. And random testing can be used in combination of smoke testing. So for instance, I know that compilers like the GCC compiler that is used to compile C++ code can or was tested using random testing. So imagine that we produce random text files, and we send these text files to the compiler. They are not code, right? A random text file is hardly code. So when I send it to a compiler, it should produce an error message, which is the correct expected output of it. But it should not produce a crash. The compiler should not crash. It should just give a syntax error, or it should produce a correct compilation. So a way of testing compilers is to randomly generate input to it, randomly generate text, and then say that this is input, and then we'll run it with it, and then and we can also do more intricate random testing. So we run, for instance, generate correct code, and then we send that to the compiler. We can randomly generate correct code and then send that to the compiler, and it should still not crash. We should not get any asserts called. We should not get any exceptions. We should get an output. It could be a syntax error still, perhaps, but correct output. So random testing is quite good. Sometimes you could also do it for web applications. You randomly generate different URLs, stuff like that, and yeah, or ask for random pages of your site, and then it should not, produce a log message or an error message. Okay, so this was the entire lecture with all its parts. So what is left for you to do this week? So if you've listened to the first course introduction and first lectures, basics of testing, the slides are on the course homepage. I will put a link to this recording also. You already got a link to the recording in Slack. There is also this TDD with PHP unit, part 0. I would recommend that for those that are going to work with assignment 1, part 2, because they are going to work with pair programming and then TDD. So the TDD part of that, not really PHP. It's not the important stuff here. Not sure if we have tutoring this week. If we have, it's in the schedule. There is this YouTube video on test-driven development by Roy Ochevero that you can look at. There is this guest lecture on Max and me. Look how happy I am. And you should read the first 3 chapters in the book. Yes. I will send out the link for the assignment ASAP, but it's a bit of script that I need to test first. So I want to send it out to a few students and then ask if they got that email, and then I'm going to send out the entire thing. Okay. Thank you very much. Thanks for today.